This presentation is called Humpty Dumpty and His Wall, and what it's trying to introduce you to the idea of impulse momentum theory. And impulse momentum theory is it's really important in terms of your everyday life, in terms of keeping you safe in a traffic some sort of accident, or while you follow through whenever you're playing sports and those sorts of things. So, great things are not done by impulse, but by a series of small things brought together. And that's a quote by George Eliot. So, we want to look at the learning goals for this particular one, and it says you should be able to understand the factors that affect impulse. Okay, so you should know what impulse is, and then you should be able to say, okay, based on the factors that affect this impulse, what can I do with it? Can I design some sort of safety device in order to keep something safe? And you should be able to use the equation right here. This right here is the J equals F delta T equals M delta V. And people get kind of confused with that because it has these two equal signs right here. But you can think of it as two formulas. Or actually three. You can think of it as J equals F delta T. You can think of it as F delta T equals M delta V. And then finally, you could think of it as J equals M delta V. They're kind of all equal to each other, so they just set it as one long equation. So we want to start off by looking at Newton's second law, and we want to expand it out a little bit. So Newton's second law, he originally wrote these in terms of momentum, not in terms of force. So he didn't come up with force and say, oh, look, I'm going to name it after myself. He didn't do that. He actually wrote it in terms of momentum. So you can actually combine these equations to get Newton's original version that he had. And if you see, it says F net equals ma and P equals mv. So if we were to look at this, V and P and M, there's a lot of similarities that go on here. So what we want to be able to do is we want to say just something a little bit different. If you were to look at F net equals M A. Now remember, A is actually the change in velocity over the change in time. That's the definition of acceleration. So if you were to look at this, you can now say, okay, I've got something that's going on here, and I'm getting pretty close to this idea right here of MV. But I need to move this t over to the other side in order to make that work. And so what you do is you multiply both sides by delta t, and you come up with the equation F delta t equals, and then you have M delta V. Now this term right here is how he actually wrote this equation. You have this idea that the change in an object's momentum is equal to the force times the time that's actually there. And this is actually how Newton wrote his particular equation. There's some disagreement of whether he left the time over here as far as divided by or he'd moved it over, but he had actually written it with no acceleration at all in this particular equation. Now, in the egg toss, which you guys did earlier, it said what factors did you do to reduce the impact force on the eggs? And so there's a couple of things that you could have done. Generally speaking, whenever you toss the egg, whoever catches it with their hand and then brings their hand backwards. Now, if you were to leave your hand rigid and just catch it, it will shatter and it will break right there. Okay, that's the most important thing. 'Cause other people, what they try to do is they try and slow the egg down as much as possible. So just barely throw it till it can really just hardly ever get there. So really you can reduce the velocity of the egg whenever it hits, or you can do what's called increasing the impact time. So in other words, you're kind of slowing it down very gradually, or your acceleration is very small. If you have something that's really rigid, it won't actually work. And other people try to use things like cushions and things like that. But there's lots of things that you can do to reduce the impact force on the egg. And those are right here. The higher the velocity was, the more likely the egg was to break. So when you first started right next to each other, it was pretty easy to get it back and forth. But as the distance increased between the two, you had to throw it with a greater velocity to get it to actually go there. Well, when you throw it with a greater velocity, that velocity has to go away. You've got to bring it back to rest. And as a result, the higher the velocity, the more likely the egg was to break. Another factor that you really couldn't control in this particular lab was that the higher the mass, the more likely it was to break. So if I were to give you a jumbo egg with a greater mass of something like 90 grams, it is much more likely to break than a medium egg, which is somewhere around 50 grams, just because of its sheer mass. Second or third, the more rigid your hand, the more likely it was to break. Not break, but to break. The more rigid your hand was. So, like whenever you caught it, your hand should have given a little bit and kind of swung back, and that makes it much less likely that you'll break the egg. Well, this is very, very similar to what we talk about in terms of car safety. Okay, in terms of car safety, the anti-lock brakes help you reduce the car's velocity. So it used to be that your brakes would, if you slammed on the brakes, they would lock up and they just wouldn't work anymore. Okay, and because of that, they wouldn't work effectively and your car speed would be much greater. Well, by putting in anti-lock brakes, what it allows you to do is it allows you to keep braking, and so you can reduce the impact time. Okay, just like we said, we're trying to reduce the velocity of the egg, we're trying to reduce the velocity of the car before some sort of impact. Okay, next what we did is we said, okay, we want to be able to reduce the mass. And that's one of the other things we did is we construct the cars out of synthetic materials. Okay, you'll hear a lot of times that cars are made of plastic now, and people say that is kind of a derogatory thing. They're not made out of iron and steel like they used to. There's a couple of different reasons why though, but yes, they are trying to reduce the mass. Couple of reasons is they're trying to keep you safer while you're actually in your car, and the second thing is it actually really helps out with gas mileage. If you think about it in terms of energy, which we just finished, okay, the less mass that's required, okay, the lower the mass, the lower the kinetic energy that you can have. Okay. Next, you have, and finally, you have what are called crumple zones. The crumple zones are the idea of rigidity. Okay, the more rigid your hand is, the more likely it was to break. The more rigid your car is, okay, if it's made out of metal and it's really solid, the more likely it is to break. The impulse momentum theory is also useful when you're trying to increase the force on an object, not just decrease. So if you look earlier, we were trying to say, okay, how can I decrease the force on a person? Well, now I want to increase the force that's exerted on a ball. And so these are some things that generally coaches tell you to do. They say, okay, make sure that when you swing as hard as you can. So you're increasing the force that's exerted on the ball. That's kind of an easy one when you're trying to hit a home run, you swing hard. But whenever you look at this, you can also say increase the contact time. Remember, we wanted to decrease the contact time in our collision because we wanted to decrease the force. But if I want to increase the contact time, what that is following through. Okay? Now, specifically, it says use a metal bat because the metal bat will impart, it's more rigid, and so it will impart more of a force in a shorter amount of time. But really, what you want to do is you want to increase the contact time as much as you can. In this particular case, you can't change the mass. You're not allowed to say, okay, well, I'm going to switch a baseball to a softball or something like that. You can't do that. And actually, increasing the mass wouldn't be very effective if you're trying to change the momentum or change the velocity of the ball. So you're not allowed to change the mass, so that's not an option for us. But if you swing hard and you follow through, that will impact the velocity of the ball. So in the first example, it says the 8 ball and a ping pong ball are dropped from a height onto a force plate shown below. Which one do you expect to show the greatest change in momentum? Now this is kind of it's a conceptual question, but you could always back it up with math. So if you were to look at this, they're dropped from the same height. So if the height is equal, then you could use conservation of energy. You could say, well, GPE equals MGH. Here, right before it hits the plate, it would have kinetic energy, which is 1/2 mv squared. And you can cancel out and say, well, mass isn't going to matter when I calculate the velocity. And it's not. Okay? The mass is not going to matter whenever the velocity of the ball is determined. Both balls will have a certain initial velocity, which is whatever it is depending on their height, but that velocity is going to be the same there. Both balls are going to have some velocity and they're going to come to a rest. Okay, we're going to assume they're going to come to a rest. You could always have one bounce or something like that, but we're going to assume that they come to a rest. If they come to a rest, the change in velocity for both of these is going to be the same. So if you were to look at this particular, in this particular case, which one is going to show the greatest change in momentum? Well, remember, momentum means mass times velocity. I can really change two things. I can change the mass, or I can change the velocity to change the momentum. Now, I'm not changing the mass in these particular cases. Okay, the mass is going to stay constant throughout. This one is going to have a certain mass. This one is going to have a certain mass. Okay, the change in velocity, they're both going to be going from a certain velocity to 0. So a lot of people say, well, since there's no change in mass and the change in velocity is the same, they're going to have the same change in momentum, and that's not the case. Okay, you can say that the change in momentum is equal to the mass times the change in velocity. So for the 8 ball, it's going to have a larger mass. It's going to have a larger mass than the ping pong ball. So because of its larger mass, it's going to have a greater change in momentum, even though it has the same mass all the way throughout and the velocity change is the same. Next, it says, why are boxers taught to roll with the punch? It's one of those things where if you look, what we've talked about so far is if this guy is punching this guy, when he exerts a force right here, if you can increase that contact time, okay, remember he's going to get hit with a certain force anyway. So if you can kind of increase that contact time, what you're doing is you're decreasing the force because you're going to have the same change in momentum regardless. Okay, the mass of his head is constant. The change in velocity is going to be the same regardless. So it's like an airbag sort of situation where you have a set change in velocity, you have a set mass. So really the only thing you can do to decrease the force is increase the contact time. So if you kind of roll with the punch, which means he's kind of going backwards as he's being hit, this time drastically increases. When you increase the time, you decrease the force or the effectiveness of the punch. Kind of the opposite is you tend to see, if you've ever seen a boxing match where somebody's knocked out in one hit, what happens is they tend to be kind of leaning forward or going forward as they get hit, and that really shrinks the contact time and it really increases the force. So that's why they're taught to kind of go with the punch as opposed to trying to kind of step into it. And this example says, why should you follow through in golf to maximize your distance when striking the ball? Well, this is exactly like we had with the baseball. So there's no set change in velocity. What I really want to do is I want to change the momentum of this golf ball a lot. I want to get it to go this way. So I really, really want to change the momentum. Now, the mass of the golf ball is set. You can't change that, but you can change the velocity. So what we really want to do is we want to change the velocity. Well, how do we do that? Well, the first thing that you can do is you can swing hard. And I know that doesn't always work in golf because when you swing hard, you miss the sweet spot and all that kind of stuff. But for our purposes, what we're going to say is the harder you swing, the more force you're applying on the ball, the greater acceleration it's going to have, and then the more it's going to change velocity. So we're going to say that when you increase the force, you increase the change in velocity. The second thing that you can do is you can increase the time the force is applied. So if you can increase the contact time that that force is applied, you can also increase the change in velocity. So how do you increase the contact time? Well, that's what happens when you follow through. When you follow through, the club is in contact with the ball for just a little bit longer, imparting more force and resulting in a bigger change in velocity and therefore a larger hit.